Hello everyone. This is our third video lecture or a last video lecture for this solution chapter. So now we will discuss the few topics left over in the solution chapter. These topics are what are azeotropes, types of azeotropes, then colligative properties, how these colligative properties are used to determine the molecular masses. Then we will discuss the purification of water, how the elevation of boiling point take place, how the depression of freezing point take place, what is abnormal molar masses. This is all what we will discuss in this lecture. So our first topic is what is azeotrope. Azeotrope is nothing but a constant boiling mixture. Okay, when two liquid mix up and they boil, then the boiling temperature will be different from respective mixtures or liquids. So for example, we can have example of alcohol or water. We can say that it both boils at different temperature individually, but when we mix them both, then we will see that they boil at a new temperature. This is the azeotropic mixture. So here we can say that if we have a boiling mixture, we have a component, a liquid, then a b component with a b liquid, then a boils at this temperature, b boils at this temperature. Both have different boiling points, but when we mix them in a fixed ratio or a mole fraction in any ratio, okay, which has this boiling point, then at this point this is very much different from the boiling point of a component or the boiling point of a b component. So this at this point we have a azeotropic mixture. Okay, now next is type of azeotrope. We have a two type of azeotrope, that is minimum boiling azeotrope and a maximum boiling azeotrope. Okay, so for this topic you have to remember our first lecture in which we have studied about non-volatile solutes. In that we have discussed that what is positive deviation, what is negative deviation. On the basis of that positive and negative deviation, here the minimum boiling azeotrope and maximum boiling azeotrope will be there. Okay, in this azeotrope or a minimum boiling azeotrope, we say that those solutions or those non-volatile solutions which show positive deviation from Rhodes law will show the minimum boiling azeotrope. For this boiling azeotropes, we have ethanol which boils at 78.4 degrees Celsius and water at 100 degrees Celsius. Okay, they both boil at different temperature, but when we mix them, we get a mixture, and when we boil that mixture, then the boiling point of that mixture will be less than both the temperatures. It will be lesser than 78.4 degrees Celsius. It might be 74, 75, but must be lesser than this. Then this type of mixture which is formed, which boils at less than 78.4 degrees Celsius, is an example of minimum boiling azeotrope. And in a maximum boiling azeotrope, we will see the solutions which show negative deviation from Raoult's law will came in our maximum boiling azeotrope. For this we have example hydrogen chloride which boils at 84 degrees Celsius and water at 100 degrees Celsius, but when we mix both liquids, then it boils at 110 degrees Celsius, which is more than both liquids. So this is maximum temperature more than 100 degree. Okay, so this is the temperature which is higher than water, which is higher than HCl. So this mixture is known as a maximum boiling azeotrope mixture. This is a graph showing the positive deviation and negative deviation. Actually, I said you earlier that the positive deviation and negative deviation we have discussed in lecture first. Okay, in solution part 1, I will show the link of that lecture in comment section also, so you can easily get the information regarding non-volatile solute from that lecture also. So this is a mole fraction of 0 to 1 component, and this shows a liquid then vapor. This is a composition, and this is a composition for this point. This is a positive deviation, means azeotropic mixture. This is also exotropic mixture. One is for post maximum deviation, one is for a minimum deviation. Okay, maximum for negative deviation and minimum for a positive deviation. Moving to next topic are colligative properties or colligative properties of solution. So our first we will discuss what is colligative property. Colligative property is nothing but a property of a solution in which all the phenomena and all the things only depend upon the solute particles present in a solution and does not depend upon the identity of the solute particles. Okay, so this is a pure solvent. Here we cannot correlate these properties, because these properties are for solution where solute is present. So first property is lowering of vapor pressure, second is your elevation of boiling point, third is your depression in freezing point, fourth is your osmotic pressure. We will discuss one by one. The first property is relative lowering in vapor pressure. Okay, so relative lowering in vapor pressure, firstly for that we have to know what is vapor pressure. Vapor pressure is nothing but the pressure which is generated by the vapors when the liquid or a solvent is heated. Okay, so the relative lowering in vapor pressure means the vapor pressure of the solvent get reduced when we add solute in a solvent. So this is a formula which is given by Abrol's law, or we can derive from Abrol's law that what is a relative lowering in vapor pressure. For that we have a demonstration that this is a beaker which contain only solvent, that is water. Here we have a solution where solute as well as solvent is present. So here lesser vapor will be there because the solute particle will not make allow a solvent to form a vapor. So the lowering in vapor pressure is here. One more example, you can see that we have two beakers. One is filled with the solvent, pure water. You can say other is the water with the solute particles. So when we boil both container, we see that there here more vapors are there. Okay, if more vapors are there, then we can say that more is the vapor pressure. But here as solute is added, so the lesser vapor will form. So if the vapors are lesser, then automatically it is seen that you can have see a look at this, that here a lesser vapor pressure will be there. So this is how solute forms lesser vapors, which automatically results in the lowering of vapor pressure. Next, okay, we will discuss one case having a three containers with A, B or C. In A we have 5 solute particles, in B we have 3 solute particles, in C we have 7 solute particles. So the question is which has minimum vapor pressure. So out of A or B we have more solute in A, therefore vapor pressure of A is lesser than B. Out of B or C we can say that lesser vapor pressure is of C because more solute is in C. Out of A, B or C, lesser will be of C because C has a more solute. So it is clear from this that which sample has the lowest vapor pressure, that it is a C with the higher solute concentration. So if solute concentration is higher, so vapor pressure will be lower. Now moving to next property, that is elevation in boiling point. So a solution boils at a higher temperature than the pure solvent, then that is known as a elevation in boiling point or elevation of boiling point. Okay, what is this? We have a graph. Okay, here is a temperature, here is a pressure axis. We can see that at 1 atmosphere pressure, we can say the solvent boils at temperature T naught P, which is a pure temperature where boiling point of a pure solvent. Okay, when we add solute, then it boils at a temperature somewhat TB. This is the temperature of the solution, and this show increase or elevation of a boiling point. Okay, the change in this boiling point is known as your elevation of boiling point, which we have used here. So delta TB is equals to Kb into M, where Kb is your abiloscopic constant, M is your molality. Okay, so here the application of elevation in boiling point is we add solute in solvent for cooking, so it will increase or elevate its boiling point, which normally used in everywhere in our kitchen, in restaurants, or everywhere where we cook food or we do household purposes. We add a salt just to increase the boiling point. Next, our third property is depression in freezing point. So depression means decrease. So depression in freezing point means that decrease in the freezing point of a solvent. So where solute is added in a pure solvent to decrease its freezing point. This is a graph for that. The pure liquid have this temperature freezing point, but after adding a solute, the solution will be at this temperature. Depression, that means pure will have a higher temperature or a higher freezing point, then after adding solute it will be lower. So the change in freezing point is your delta TF. Okay, now moving to next. This is a scenario of say things that here is a solvent and solute particles trap the solvent, so it cannot get evaporate easily, so they lower its freezing point. Now the real life examples for this depression in freezing point is that we use coolants in radiators of automobiles just to cool down the system and just to decrease its freezing point, because in areas in a worldwide we have a places where the temperature is lesser than 0 degrees celsius. In that places you can see that the vehicles move. So that reason is that because of this antifreeze coolant, which is your ethylene glycol, mixture of ethylene glycol and water. Okay, the next usage of salt used by the ice cream mans, ice cream vendors use salt to make ice cream so the ice cream will not melt easily. So this is the help of this depression freezing point in a daily life. So next property is your osmosis and osmotic pressure. Osmosis is nothing but the movement of solvent particles from a region of a higher to a region of lower concentration through a semi-permeable membrane, or we can say that from a region of lower concentration to a region of higher concentration through a semi-permeable membrane, in which solvent will always flow from a more dilute solution to a higher concentrated one. So don't mix match these things. Osmosis is nothing but a movement of a solvent from a lower concentration to a higher concentration of a solute particles. Okay, lower concentration of solute to the movement of higher. So we can see this. We have a semi-permeable membrane and we have a solute particles. Here concentration is higher, here concentration is lesser. This blue represents the concentration of solute. Here this purple represents the concentration of solute. Here solute is more, here solute is lesser. So this is dilute solution, this is concentrated solution. So the when osmosis occur, what we see that the solvent move from dilute side to the concentrated side and the level of a solvent decreases here. This is what osmosis is. So what is a semi-permeable membrane? It is a membrane which allows the solvent particles to pass through it and does not allow our solute particles to move. So in semi-permeable membrane, we can see that for freshening of water or for you can say purification of water, what we do, we put pressure towards the opposite side where the solvent move. Then we can see that the water from this salt water move to the fresh water side by passing through the semi-permeable membrane. This pressure is osmotic pressure. Okay, so related to osmosis, there is one term diffusion. The difference between diffusion and osmosis is nothing but here in osmosis and diffusion one thing is different, that in osmosis we need semi permeable membrane, but in diffusion there is no need of semi permeable membrane. In osmosis the particles move from the solvent move from lower concentration to higher concentration, but in diffusion the particles or solute move from, you can say the movement is from higher concentration towards the lower concentration. This is a difference where osmosis, here is a diffusion. You can check easily here, semipermeable membrane is required, not required. Spreading of ink in a drop of water, you can do it by your own at your home. Even nowadays to just put one drop of ink in a water and you can check. If you don't have a ink, you might be thought that we don't have ink, then you can use a one drop of Dettol in water and you can check the diffusion. Okay, so in osmosis you can see the shrinkage of potato slice when it is kept in a sucrose solution. So this is osmosis. Even a best example of osmosis is what we do, we water roots or plants, so the water from the roots get to the leaves is just example of osmosis. Even vegetable vendors sprinkle water in the evening to make or to remain their vegetables fresh is another example of osmosis, where the semi-permeable membrane is your layer or the natural membrane outermost covering of the vegetables. So this is a reverse osmosis which is used by you at your home for RO system or the purification of water. What they did simply, we have a pure water in a one side, we have a semi permeable membrane, we have a salty water or a sea water. When we don't apply pressure, we can say water from this side move to this side, as here salt is lesser or no salt is here, so movement from this side to this. But when we apply pressure here, then the water from this side start moving from this to this side. This is the process by which we purify water. This is what demonstrated here. that we have a salt water, then we apply pressure. This salt water when compresses, salt gets separated here, water from this semi permeable membrane moves to this side, and from this side we can use or take our drinking water. Now I think now you understand the osmotic pressure. So osmotic pressure is nothing but the tendency of or the capacity of a pressure to stop the osmosis and reverse it. Okay, so this is a sum up of colligative properties. These four colligative properties we just discussed. Now next is our for abnormal molar masses. Abnormal molar masses are the masses which we think of that they exist, but then here we know how they exist or they don't exist. Okay, these masses basically exist for your electrolyte things. Okay, for electrolytes, because electrolytes can dissociate, electrolytes can associate. If electrolyte dissociate, AB is your electrolyte, it dissociate A negative and B positive, so the number of particle increases. Let's say we have one electrolyte AB, it dissociated and it formed two anions. Okay, one ion A negative, one ion B positive. So in dissociation, particle increases. In association, two particles combine to form one particle, so number of particle decreases. This is what we see, this Van 't Hoff factor. Here we see normal mass, normal molecular mass divided by abnormal molecular mass, which is a observed colligative property divided by calculated property. Okay, so by using this formula we can calculate I. For association, I is less than 1. For dissociation, I is more than 1, because number of particle increases in dissociation. And for no association and no dissociation, that is for known electrolytes, this I will remain 1. For example, for this association dissociation, when 1 mole of K2SO4 put in water, then it dissociates and divided into three parts. Okay, so I will be 3. When 1 mole of acetic acid combined in benzene, put in benzene, then it combined with other molecule of acetic acid, then it get associate. So from 2 we get 1. So 1 by 2 is I for Van 't Hoff factor for association. So this is all what we discuss in this lecture, and by this we will end our chapter solution. Hope you like this lecture and understand each and every topic. Thank you.